Hello everyone. So in the last session we discussed about empirical distribution with based on the rank how we compute the PDF, CDF, based on the histogram, and then we kernel based. We can also use theoretical distributions. Of course, when we have the data collected or some observation we have, we need to see which theoretical distribution is matching with the data we have. So before we go into matching, let's start with some theoretical distributions. Two of the theoretical distribution we have been using. We were using uniform distribution, we were using normal distribution. So let's start with the normal distribution. We'll use the stats library of scientific Python. So it has several parameters, but two of the main parameters are location parameter and scale parameter. So first what we are doing, we are generating a different instance, not the distribution. Okay, maybe you can print it so you will know what we mean by instance. Print rv1, printing it. So you see it's referring to something, but it's not exactly some variable or some data something is there. So there are three instances of the normal distribution with location 0 and scale parameter we have taken three different 5, 3 and 7. Now we will generate different value of x minus 50 to 50, and we are generating thousands of item between minus 50 to 50. Now using the instance we have defined in the earlier part, we can compute the PDF. So we are computing the PDF for all the three instances, and now we will plot it to see how the three instances are how the three PDFs are looking different. So we have the PDF in in the blue color with 5, then we have a orange color 3, and we have the green with scale is equal to 7. So what is happening when the scale parameter is high, our spread is becoming high, so data has more variance. Whenever scale is low, our data has low variance, like you can see for the scale is equal to 3. For a normal distribution, our variance or standard deviation is the scale parameter. For some distribution it might be different one also. Now let's look at what is the scale parameter with the location parameter. So we'll go again, and maybe this time we can keep same scale, and we can change the location. Let's say we take 0, 5, and then we can take 10. Let's try to rerun it. We need to correct our legend, because now the scale parameter, we are changing the location parameter, not the scale parameter. So what is happening, as we are changing the location, our curve is shifting to the left and right. And for a normal distribution, our mean is the location parameter. So location parameter means how the mass of the is changing to the left or the right, so that represents the location parameter. Scale means which are talking about how it's varying, it's very in the very narrow or it's very wider, so that is our scale parameter. We can use same thing to compute the CDF using the same instance. So here we have three different location parameter, not the scale parameter. So let's change it to scale parameter 5, 3 and 7. 5, 3. So I due to limited time, I try with one parameter, but you play with different parameter, and then you try to make your understanding how it creates the difference, how the different location parameter, how the different scale parameter make the change in the in the CDF or the PDF. Maybe we'll take the same location parameter, so it's easy to understand one parameter by one. When you mix too many, it's not so easy, at least in the beginning, to figure out what is causing the change. So you can look at the 3 CDF. When we have the large scale parameter, that is the green color, you can see there is a more spread in the CDF. it's going till here, the large part, and then it is starting from the beginning, it's rises. So we have the more data point between this and this range. For the lowest scale parameter, that is the orange color, you can see the range is very narrow. So you can try to understand how the location parameter, how the scale parameter make the difference in the CDF also. So because CDF is the integral of PDF, there are slightly different way to interact it. Like when we see a flat line, it means there are not many data points or nearly zero data point between this range. We can use the same library to different to generate other distribution, like we'll take Cauchy, chi, exponential and uniform, and this is the same way you can define, and we can make a plot of it. So for this also you can make a plot of PDF, you can make a plot of CDF. You can look at the uniform distribution. We know uniform distribution has a support between A and B, and outside that it has no chance of coming it. So you have the PDF is 0. In the you can see how the exponential, it's slowly it's decreasing. How the Cauchy is more similar, symmetric distribution, very similar to a normal distribution, but there are some differences. We'll look at it, what are the differences sometime. And there is a chi distribution, that is also a not similar to normal distribution because it's not symmetric, but the shape is not very different from the bell curve. Now in this, what we are trying to do is, what you can try is you try to generate different kind of the different number of variable. You can try with 10, 100, 1000, 10,000, and see how nicely or how poorly they represent the PDF or CDF. So we are taking the normal distribution with some location parameter and some scale parameter, generating X like we have been doing, and we generate some random number and see how the histogram is looking and how the theoretical curve is looking. So you can see when we are starting with 100, it's yellow color, not so clear, but you can see there are few points which are departing from this theoretical distribution line, that is the red color line. As we increase more and more number of variable, our the data is fitting very well the the theoretical distribution. So in real life, typically we don't have tens of thousands of samples. There may be very few the example where we have so much data set. Largely we deal with some 100, sometimes even less than 100 data set. So we don't get a very nice curve which matches with the theoretical distribution. So but there are ways, not only visualizing, how we can compare whether our data is fitting some distribution well or not. So in the next exercise we'll discuss about that. I have taken only few example, but you go through it to that also, okay, to try some other kind of distribution and see. Some may be converging very fast, some takes much more number of data point to converge. This you can see for other kind of distribution, how many number of variable we need to perfectly match it. So you try it, I have tried with two, you try with more and see how much time it takes. And in the next sessions we'll see how we can compare to distribution even when we have less number of data point, more than just visualizing the data, and see whether we are our data belongs to some distribution or not. Thank you, see you next time.